Welcome to our Lesson 2 in Random Variable and Probability Distribution. In this video, we will focus our discussion in the probability distribution of discrete random variables. In our previous discussion, we have learned how to determine the possible values of our random variable x. Now, it would also be useful to know how this variable behaves in a repeated observation. What would be the most common value of our random variable? What proportion of the time would the random variable x be equal to 5? How about when x is equal to 3? In this lesson, we will use a probability distribution to provide us such information, especially about the long-run behavior of a random variable. The probability distribution of a discrete random variable, denoted by uppercase X, gives the probability associated with each possible x value, denoted by lowercase x. Each probability is the long-run relative frequency of occurrence of the corresponding x value when the chance experiment is performed a very large number of times. Common ways to display a probability distribution for a discrete random variable are a table, a probability histogram, or a formula. Frequently, it is convenient to represent all the probabilities of a random variable x by a formula. Such formula would necessarily be a function of the numerical values x that shall be denoted by f as a function of x, or read as f of x, g of x, r of x, and so forth. Therefore, we write f of x equals to p of the random variable x equals to lowercase x. Say for example, if we want to know the probability of the random variable x when it is equals to 3, we denote f of 3 equals the probability of x equals 3. The set of ordered pairs x and f of x is called the probability function, probability mass function, or the probability distribution of the discrete random variable x. We take note the values of the ordered pairs lowercase x and f of x. These values will be used to create the probability histogram where the lowercase x will be in the x-axis and f of x is in the y-axis. Let us take note of this definition. It states that the set of ordered pairs lowercase x and f of x is a probability distribution of the discrete random variable x if, for each possible outcome lowercase x, f of x is equal to or greater than 0, the summation of all the f of x's is equal to 1, and the probability of the random variable x at a value lowercase x is equal to f of x. To understand more the topic, let's try to solve the following problem. Suppose that each of 4 randomly selected customers purchasing a refrigerator at a large appliance store chooses either an energy-efficient model, E, or one from a less expensive group of models, G, that do not have an energy-efficient rating. Assume that these customers make their choices independently of one another and that 40% of all customers select an energy-efficient model. Find the probability distribution and the probability histogram for the number of energy-efficient refrigerators purchased by the customers. Based on the problem, we denote E to be the event when the selected customer purchases an energy-efficient refrigerator, and G when the selected customer purchases a less expensive one. Then, the probability of E is equal to 0.4. This means that the probability of G is 1 minus 0.4. And that is equal to 0.6. If we let x be our random variable, where x is the number of energy-efficient refrigerators purchased by the 4 customers, then for this problem, the random variable x has 5 possible scenarios. First, that is when there is no energy-efficient refrigerator, E, is purchased by the 4 customers. Second, when only one E is purchased. Third, when only 2s. Fourth, when only 3s. And lastly, when all customers buy energy-efficient refrigerators. So therefore, the possible values of the random variable x are 0, 1, 2, 3, or 4. First, let us consider when there is no E being purchased by the 4 customers. The possible combination will be G, 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 and G if we get the probability. Since these are independent events, we will multiply the probabilities of G, that is, 0.6 times 0.6 times 0.6 times 0.6. Therefore, the probability that the 4 customers selected did not purchase an energy-efficient refrigerator is 0.1296. Another possible experimental outcome is only one customer selects E. One possible outcome will be E, G, G, G. Then, the probability that the last customer selects an energy-efficient refrigerator is 0.0864. The possible outcomes can be G, 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 E, G, G, E, G, G, E, G, G, and E, G, G, G. Since there are more than one possible outcomes that has only one E selected, how do we determine the number of these possible outcomes? The answer is through combination. Since it doesn't matter what the order will be, we will use combination to calculate the number of possible arrangements. The first term in the equation refers to the number of possible arrangements. It could be GGGE, GGEG, GEGG, egg. Then we will multiply it with the probability of E, which is 0.4, and the probability of G, that is equal to 0.6. Calculating, we get 0.3456. Therefore, the probability that one customer selects an energy-efficient refrigerator is 0.3456. Another possible experimental outcome is when only two customers select E. One possible outcome will be G, G, E, E. Then, its probability is 0.0576. We then calculate the number of possible arrangements when there are two S selected. That is 4 factorial divided by the product of 2 factorial and 2 factorial, which is equal to 6. We multiply this value to our previously calculated probability, which is 0.0576. Therefore, the probability that two customers select energy-efficient refrigerators is 0.3456. Following the same process, we get f of 3 equals 0.1536. And f of 4 equals 0.0256. Based on our calculated values, we can now create a probability distribution table as shown. We then plot the values generated from the probability distribution table. We plot the values of our random variable x in the x-axis against their respective probabilities. The figure shows the equivalent probability histogram of the random variable x. We might also be asked, what is the probability that at least one customer will purchase an energy-efficient model? This means that either 1, 2, 3, or all the 4 customers will select an energy-efficient model. Then we can interpret as is finding the probability that the value of the random variable x is greater than or equal to 1. To solve, we will calculate f of 1, f of 2, f of 3, and f of 4. The resulting value is 0.8704 or 87.04% chance that at least one customer will purchase or select E. Now, it's your time to answer the following problem. Let X be the number of courses, or subjects, for which a randomly selected student at a certain university is registered. The probability distribution of X appears in the following table. When uppercase X is 1, the probability distribution is 0.02. When X is 2, the probability distribution is 0.03, and so on. Here are the set of questions. A. What is the probability distribution, or what is f of 4? B. What is the probability when x is less than or equal to 4? Or, we can ask, what is the probability that the selected student is taking at most 4 courses? C. What is the probability that the selected student is taking at least 5 courses? And D. What is the probability that the selected student is taking 3 to 6 courses? Beside each question, in color green, is its respective answer. Get your pen and paper and show the solution to these questions. Thank you for watching and see you in the next video.